Oi, Ana Rita.
Hello.
Como está?
It's better to switch off the camera for the other people. Ok. So, boa tarde a todas e todos. Eu sou a Pamela Pavaneto. Sou professora visitante da UFO e quero dar boas-vindas a mais um encontro do ciclo do projeto Sedimentando Conhecimentos Geológicos na Quarentena. Esse projeto é um projeto de extensão do curso da Geologia da UFO. É um projeto que foi idealizado pelo professor Luciano Alessandretti, que veio a participação da professora Liliane Ibrahim, do professor Félix Nanini, do professor Marco Delinardo, do professor Emerson Almeida e do professor Daniel Sedorco, além da minha participação, claro. Esse projeto pode acontecer também graças à nossa equipe técnica de estudantes, a Raquel, o William e o Pedro, que estão conosco hoje, que vão cuidar da parte logística e vão disponibilizar na chat de YouTube o link para o certificado. Ou seja, os alunos que precisarem de certificado vão encontrar na chat de YouTube. Agora, finalmente, vou apresentar o nosso convidado especial, que é o professor Uwe Reimold. Uwe, I'm so glad you accept your invitation. And I'm going to introduce you in Portuguese. I try to resume your huge curriculum vitae. So, o professor Uwe, antes de chegar como professor titular livre da Universidade de Brasília, ele foi docente na Universidade Humboldt de Berlim, da Universidade White da África do Sul e da Universidade de Münster. Ele possui mestrado e doutorado em mineralogia pela University of Münster, na Alemanha, e doutorado e pós-doutorado pela NASA no Johnson Space Center. Como eu já antecipei, o currículo do professor Uwe é incrível. Vou tentar de resumir aqui. Ele é membro de corpo editorial da Geological Society of American Bulletin, da Planetary Science, é revisor de diferentes periódicos, entre eles Geoquímica e Cosmoquímica Ata, Science, Earth and Planetary Science Letters, Journal of African Earth Science, Terra Nova, Tectonophysics, European Journal of Mineralogy e muitos outros, né? As áreas de atuação, como vocês podem ver dos periódicos que eu mencionei, são principalmente em petrografia, crateras de impacto, geocronologia e geoquímica. Atualmente está envolvido em vários projetos de pesquisa internacionais e vou mencionar aqueles que ele está na liderança, junto com a equipe também do Brasil, incluindo a professora Natália Hauser, da UNB. Desde 2015, começaram um projeto muito importante que veio análises isotópicas de rochas, de estruturas de impacto e brechas pseudotaquilitos, né? A comparação entre dois dos principais crateras, que são a cratera de Araguainha, que atualmente é a cratera conhecida mais importante da América do Sul, maior, e a cratera Vredefort, que é na África do Sul, que é considerada atualmente a cratera maior do mundo. Entre outros projetos que envolvem análise de estruturas de impacto, tem um projeto de pesquisa em Nova Colinas, no Maranhão, considerada a nova estrutura de impacto do Brasil. Além de estudar em Brasil e África do Sul com esses novos projetos, atualmente tem um projeto de pesquisa em estrutura de impacto também na França, Rochechouart, se não errei a pronúncia francês. Então, eu estou muito agradecida para o Uwe participar do nosso ciclo de palestras. E agora vou passar a palavra para ele para apresentar a palestra Impact Cratering An Introduction to this Fundamental Planetary Process. So, Uwe, many thanks with you a talk.
Thank you very much, Pamela. Very kind introduction. It's because I'm so old, I've done a lot of things, but anyway, it's not finished yet. I'm very happy that I can welcome those that are here, and maybe in due course we will get a few more, but let me just interrupt for a second and compartilhar a palestra.
O microfone acho que está desligado. Switch off the microphone. The microphone.
Okay. Microphone. On.
Now it's okay. We can hear you.
Okay, but I just lost. Okay, we're back in business. Okay, but we want to start at the beginning. Okay, so the title of the talk is Impact Cratering, an Introduction to the Fundamental Planetary Process. I think I go out of this so that you can see the pictures completely. The picture here is an artist's impression. Can you hear me?
Just for a moment. Yes, it's no... it's your tela, it's your screen?
Yes.
It's no...
It's not sharing
no,
with us.
YouTube, no.
No.
Oh dear. My IT specialist has just left here.
Yeah, it's okay. We wait.
But yeah. Salvana Nuwe. We'll try again.
Yeah, no problem.
But where is the talk now?
Yeah. O compartilhamento da tela.
We'll find it.
It's no problem. Just we are resolving here.
So, maybe.
Yeah. So,
Uwe, I think you just can click in the arrow at the left up corner, the orange area, in the left part up of your screen. But the leftmost part, upmost left, there's an arrow.
Up here?
Yeah. Then you will return to the presentation.
It's saved. Once more, maybe?
Yeah.
Okay. All right, let's try this one again. Okay, everybody ready?
It's perfect.
Yes.
Yes.
Okay, yes. We have not progressed beyond the title slide yet. We are still looking at what I'm supposed to talk about. This is an artist's impression of a protoplanetary disk. There are some gaps indicated which indicate there's planetary formation. And what was happening in the protoplanetary disk, tiny dust grains were impacting onto each other. And they were sticking sometimes to each other and become bigger. And this would progress to snowball size, to block size, to planetesimal size, maybe up to 1,000 kilometers in size. And then minor planets, 1,000, 2,000 kilometers in size. And eventually these things would aggregate, agglomerate, come together and become planets. And this is what would have happened in the very early stages in the first 50 to 100 million years of the development of our solar system. Maybe now I can enlarge the picture. Yes. So here we have a false color image of one of the probes that mapped out the moon. You can see what you normally can see on a full moon. Actually, it's not bad at the moment. We're just past the full moon of this month. You can see the Maria, which are indicated here in different colors, but you can still see them as the large, colorful basin features. There's another one in the upper right here. And then we have a bunch of smaller crater structures, in fact, several hundred thousands, which I cannot enlarge here on this picture. And we have information about ages on these structures. We have 3 or actually 4 craters with beautifully preserved ejector rays. There's one in the upper left, one in the center left, one in between forming a perfect triangle here, and one at the bottom. The one at the bottom is called Tycho and is thought to be 1 billion years old. And the ejector rays extending across one of these basins. And if they would go a little further across these basins here in the northeast as well, which means that these basins are much older. And in fact, rocks from there have been dated to 4 billion, 4.1 billion, this one here, 3.8 billion years. And we've got little C here, which is a crater called Copernicus, also relatively young. People think maybe 100 million years. And there he is. Copernicus crater of about 100 kilometers diameter with ejector rays which are much, much longer. And it shows what a fresh, not so strongly eroded, complex impact crater looks like. It has a nice rim feature, which we can still see raised, and raising here means probably 1,000 meters or 2,000 meters. We have these structures in the center, a range of hills, which probably is 3-4 kilometers high from the base of the crater. And we've got the collapse along the inner edge of the crater structure. And if we would be at Araguinha now, we would visit the central uplift of the crater. We would see the ridge, actually, quite eroded, but still visible. And we would definitely see some beautiful terrace features on the inner side of the southwestern rim of this largest impact structure in Brazil and the largest impact structure known today in South America. Here we have some simple bowl-shaped structures that do not have the central uplift and are simply called simple. On Venus, we cannot see so many impact structures. What we see are a few volcanoes, like this one here, just to the north of the center. You can see lava flows in this mosaic image of imagery from the Magellan radar probe that managed to look through the dense atmosphere of Venus. But here on the east, we have a large impact structure. There's another one with a slightly lighter rim, and there are some beautiful impact features on the surface of Venus. But there are many less than on the moon. And the simple reason for that is that the surface of Venus is only a fraction in age from the age of the moon. People think that Venus was completely volcanically resurfaced about 500 million years ago. But back to impact structures. We have this one here that is not complete in the northeast. And that's because the projectile came at a very low angle. It actually scraped the ground. There's no crater rim in this area. And then exploded, producing the ejecta blanket over 3/4 of the circumference of the crater. The right, much larger structure, 280 kilometers across. That's actually the one that I pointed out on the previous slide. It's completely covered in the interior with melt. You have a flat surface which represents impact-generated melt. One of the questions that people who are interested in impact cratering are, of course, fascinated with: what is the danger for us today on Earth? And this is a compilation, a recent compilation, maybe 2 years old, maybe only about another 200 or 400 lines, orbits of asteroids have been added since, so this is pretty up to date. Here we have the Sun, Mercury, Earth, indicated here, this Venus, Earth, and Mars, with their orbits around the Sun. And we've got the interfering orbits of something like 10,000 or more asteroids. Some of them have highly eccentric orbits. They will get close to Jupiter, and Jupiter's gravitation may change their orbit onto a path to cross that of Earth. But you will not be able, if I would ask you now to count the number of intersections of orbits of asteroids with the Earth orbit, you cannot estimate how many there are. At the moment, we do not have a possible projectile that might penetrate the atmosphere of Earth, but in the future, it may happen. And there's certainly need to keep an eye on things in the sky. Okay, this is an old crater chain on one of Jupiter's moons, Ganymede. We have an icy surface. You can see old impact structures, some of them polygonal, many round, and then we have this chain of craters. And we had another chain of craters that at least some of us can remember from July 1994. We had a collision of pieces of Comet Shoemaker-Levy 9 with Jupiter's atmosphere. And let me tell you, these little fragments measured maybe 120, 150 meters across. That's nothing. That's the size of a large office building. And each one of those made a hole like the one on the left here in the atmosphere of Jupiter. And the diameter of this hole is 12,000 kilometers. And we have several such impacts shown on the side here, making a chain of these holes. 12,600 kilometers diameter is the diameter of our planet. So Earth would have snugly fit into one of these holes. And the projectiles were only 120 meters in size. Obviously, the atmosphere is gaseous, and on a solid body, a 120-meter projectile would perhaps left a 1.5 or 1 kilometer size impact, depending on the density of the projectile. Apart from that, well, apart from maybe our species' survival, there is other importance for this process to be studied and to evaluate what happened in the past. We have looked at the numerous craters on the moon. We can count them. We can determine ages of surfaces from the numbers of craters, because we have some absolute ages for lunar rocks to calibrate this surface dating. We've got another crater here, another number of craters on a densely bombarded surface, another Jovian moon. We've got a single terrestrial crater here on the right in the Namib Desert of Namibia, Rotakam. So I could show you many more pictures of planetary surfaces. Impact cratering was a fundamental process throughout the solar system. And now that we know there are other solar systems out there with exoplanets and so on, beyond impact cratering has taken place as well. Right at the beginning, I talked about the fundamental accretion process that is nothing else but impact. Little particles, big particles sticking together and eventually impacting each other. Planetary buildup was a runaway process of impact events. Impact cratering is a fundamental surface geological process on all solid bodies. Remember the second slide, the false color image of the moon. The different colors meant different compositions of rocks. So there were some in warm colors and some in cold colors. Warm color would be red, for example, and cold blue. And this stands, in this case, for the amount of iron in the system or on the surface, in the surface rocks. So impact provides information on the planetary compositions, and maybe in craters on Mars, we can look beyond the surface and at least a kilometer down into the craters. On the early Earth, impact cratering took place all the time. We had the same kind of bombardment 4.5, 4 billion, 3.8 billion years ago as the lunar surface. But because we have a dynamic planet with plate tectonics, subduction, and only 150 to 200 million year old seafloor available over about 70% of the terrestrial surface, we don't see much of the impact history anymore. The bombardment history has all but been obliterated. It was impact in primordial times, as soon as our planet formed, that transferred kinetic energy onto the proto-Earth, providing a lot of heat for proto-Earth and the other proto-planets as well. That would make a huge contribution to the fact that the Earth would melt to a large degree and be able to differentiate internally, forming the core, forming the mantle, and forming the crust eventually. It is thought that impacts of asteroids and comets brought a huge amount of water onto the proto-Earth. But now there is a debate that maybe much of the Earth's water was already in the Earth's primary material. The transfer of life between planets has been investigated with active impact cratering experiments. Little projectiles with spores of fungi, microbes on the top, would be impacted onto rock samples, and then they would count how many microbes, how many fungal spores had survived the temperature flash upon impact. And it's been shown that impacts of 50 gigapascal pressure, of generating 50 gigapascal pressures, that's 500 kilobars, could actually still lead to survival of primitive life. So maybe we are all the result of such natural, very large impact experiments with material, with bolides from other parts of the universe. We have spheral layers in the rock record of the Archean, in the Barberton Mountainland in southern Africa, in the Pilbara Craton of Western Australia, and maybe amongst the piles of Archean early Proterozoic rocks in Brazil as well, but they still need to be discovered. There are these little particles here which are thought to be droplets of molten rock, which most likely are the result of impacts, and they contain huge amounts of platinum group elements, huge amounts in terms of up to several thousand parts per billion. And these are absolute telltale signs of meteoritic components. So we have impact deposits dating back into the Archean crust on Earth, and they tell us a lot about impact processes, which projectiles existed, and they tell us something about the target rocks and which processes affected these deposits, like tsunamis, for example. And then, of course, impact has been a fundamental process regarding the evolution of terrestrial life. First, we had intense bombardment of the terrestrial crust. Then we developed an atmosphere, and some of the smaller projectiles were filtered out. We developed a hydrosphere, and maybe during this early time, primitive life was frustrated by the intense heat and other side effects of very large impact events. Then in the Cambrian, about 650 million years ago, we had an explosion of life. Why? Maybe because that's when the reduction of impact intensity took place. The Earth became a more benign place to live on. What about mass extinctions? And after each mass extinction, there is a good chance to have enhanced diversification of life forms again. Well, all these boundaries in the biostratigraphic record, the KP, Cretaceous Paleogene, Permian Triassic, Triassic Jurassic, and Jurassic Cretaceous boundaries have been looked at, but only in the case of the KP, the Cretaceous Paleogene boundary, do we actually have a culprit, a smoking gun to point at. But interestingly, at the end of the Triassic, there were a number of impact events. They are small, but maybe we're missing the large one that needs to be added. And at that time, the era of the dinosaurs was started, maybe with a bang. Okay, on the right, we have a poster from the movie Deep Impact, scaled to the size of Manhattan Island. And on the left, we have 2.5 billion year old stromatolites. Each one of these domes is a 5 meter high stromatolite from southern Africa. And the cyclist just cycled past, and she was asked to be a scale bar. So at 2.5 billion years, there was also an explosion of life. We have no impact evidence for that time. But of course, we know that some other things were happening at that time, like massive oxygen being generated from the sea. Impact is of fundamental economic geological importance. We need impactites, such as materials available on asteroids for construction of space stations, and I mean big space stations. If Earth becomes too small for us, we may have to go to Mars or somewhere else, and we will need construction material, which is readily available. For steel production, there is a lot of magnetite in the outer 20 meters, which already have been crushed, the lunar regoliths, crushed by being impacted and re-impacted up to 15 times. On Earth, we have numerous impact structures, about 60 or 70 with economic ore deposits. There are two big ones that I can point out. There is the Witwatersrand gold, which you know as the Witwatersrand gold fields in South Africa. And there's a lot of uranium involved as well. This deposit was already there when the big impact occurred at Vredefort. I will show you where this is on the map. But the impact caused downfaulting of the existing deposits and covering it with a thick cover of ejecta. The second case of ore formation in a direct giant impact took place at Sudbury in Canada, which is known for its important nickel and platinum group element deposits. Progenetic deposits in impact structures are those that are already there prior to an impact, but the Sudbury deposits were the result of the impact. The metals were disseminated lightly in the rocks that were molten, and these molten rocks were differentiated so that at the base of this thick sheet of impact melt, there are now mineable deposits with enormous volumes of nickel and other elements. We have hydrothermal ore deposits in many places, gold, for example, in Sudbury 2. At Siljan in Sweden, a small structure, maybe 60 kilometers in diameter in comparison to Fredefort 300, Sudbury 200. Siljan still has lead zinc deposits that have caused development of a 300-year-old crystal glass industry and many other impact deposits. And impact is beautiful for education. You can take students to fascinating places in the world. Here's again Rotterdam at night, the crater in Namibia. Here we have Rotterdam in the desert from space. It's a natural laboratory for planetological processes. It's a natural laboratory for the study of terrestrial geological processes. We got water reservoirs, we got hydropower stations at impact structures, dimension stone quarries, phyllosilicate deposits, numerous economic deposits. Okay, I need to breathe. I'm going to show you now a few pictures of impact structures. Some well-known ones, perhaps this one here in Arizona, in the United States, which is Meteor Crater, also known as Barringer Crater. You see it's not round, it's square. And that's because we have two very prominent joint systems in the target rock, or in this whole region here. It's a small structure and very young, fresh. It's a strongly raised rim, upturned beds along the rim. Here you can see it nicely, 50,000 years old. Another structure here on the lower right in South Africa, Tswaing, which means place of salt. There has been a long life salt lake in the interior. The rim is degraded, it is rounded compared to the rim of Meteor Crater of exactly the same size. This structure is 4 times as old as Meteor Crater. And here's another one in Australia, also small. You can see they all have simple bowl shapes. They have more or less sedimentary deposits inside, but you can still see the beautiful rounded crater rims. And here we have part of the ejector blanket surviving, despite the fact that the structure is even older than Meteor Crater Tswaing. That's all. Rotterdam, my favorite in the desert, 5 million years old, 2.5 kilometers in diameter. The sands are shifting all the time, revealing new outcrops of impact rocks, which I'm going to introduce to you later, but also new outcrops of ejecta in the surroundings, in the desert, and of the local basement. And here we've got a somewhat older crater. The age is not known, but probably 20, 50 million years old, called BP, because the discoverers were geologists of the oil company of the same name. We have a little central uplift, which is here in the foreground, and all these hills are part of the crater rim. There are some cars for scale. Then we got funny things with terrestrial impact structures. We have 2 lakes in Canada, West Clearwater with a ring of hill of islands, and East Clearwater with basically no islands. The one is 36 kilometers, the west, and 26 the east kilometers in diameter. And for a long time, we got the same ages of 290 million years for both of these structures, because we are impact melt rocks exposed here, and they've been drilled in the interior of East Clearwater. But now, new dating has shown that East Clearwater, this one here, is 460 million years old, apparently. I don't believe it yet, because the 290 million years for East Clearwater was one of my earliest projects when I was still a PhD student. So, we go back to East Clearwater. By the way, there are several pictures here which are combinations of the so-called Tandem X. Tandem X is a radar satellite pair that was flown by the German Air and Space Agency and underlain, actually it's Sentinel-2 spectrometric data from another German satellite overlain by the Tandem X digital elevation model. I will show you several of those. Here we got Chesapeake Bay structure. It's interesting because it's just a small jump from Washington, D.C., which is located roughly up here. And it's an interesting structure. Not only has it a strange shape, the shape of an inverted sombrero, because we have an inner basin which is much deeper, shown here in cross-section, than the outer basin, which is probably caused by the massive resurges of ocean water that took place in this shelf environment on the northeastern seaboard of the United States. The other interesting thing is that the water resources along this part of the North American coastline is highly salty. And there are about 5 million people living in the environs in Norfolk and other cities around the Chesapeake Bay structure. And their livelihood depends on fresh water. And the impact has made it very difficult for these huge communities to obtain sufficient fresh water. So impact, even if it was 35 million years ago on Earth, may still cause very complicated situations for the societies, for the communities on our planet. This nice picture is a larger structure, Manicouagan in Canada, 100 kilometers in diameter. Again, we have this combination of Tandem X and Sentinel-2 data, but what we see here is a frozen ring. Actually, two lakes which were connected artificially, and they follow the ring basin around the central uplift, the elevated area of this large impact structure. And they provide hydropower for the entire state of Quebec, or province of Quebec in Canada, which is a large number of people. And here we have Sudbury. Sudbury does not look round. And why? Because we had two orogenies taking place in this area, collisions between parts of the Canadian Shield. The one to the north is the Superior Province, and then we got this part here to the south, which actually is formed by Huronian sediments. And it's the Huronian orogeny that caused this squishing together with extension in northeast-southwest of the originally round or maybe slightly elliptical Sudbury impact structure. And the whole impact structure is much larger than what we see here. This is only the extent of the molten material, the impact melt rock that now is solidified. And the ring of mines follows the southern end, and there are a few dotted on the northern edge of this Sudbury igneous complex, and others follow along these dikes which have intruded off. Here's another long one to the southwest of the igneous complex, which really is not proper igneous, but the material behaved according to igneous petrology. And here's the really big one, the largest one we know on Earth still. It used to be the oldest one, but it was pipped in age just 8 months ago by a little 6.5 kilometer structure in Australia that is 200 million years older than this one. This is Fredefort, the Tandem X image, and all we see is the central uplift of about 100 kilometers diameter. Here we can see a little bit more, and there's actually Johannesburg in the northeast. So Johannesburg is sitting at the edge of the structure, and it extends through the entire Witwatersrand basin of economic importance. We have the central uplift deeply eroded because the structure is 2 billion years old, 2020 million years old. And here we have Chicxulub, the culprit that caused the demise of the dinosaurs. and many other species, and made it possible for us mammals to populate this planet. And all you see on surface is this very faint ring in space imagery of cenotes, sinkhole structures, which show the southern edge of this impact structure. This big picture is the Bouguer gravity map. You can see we have a ring structure, we have a ring basin here, there is actually a central ring. This impact structure has a peak ring, not a central uplift. Now somebody is working on our roof on the top. The age is 66 million years, which is exactly the age of the mass extinction at the Cretaceous Paleogene boundary. This is the entire record of impact structures known on Earth. Every little yellow dot is an impact structure, which has been confirmed by its telltale criteria, which I will introduce to you shortly. There are some red dots as well, which are structures that have been called impact structures, but require further confirmation. Let's have a quick look at South America. I have a magnification of our continent at the end of this talk, but we have 7 confirmed impact structures in Nova Colinas, which I know it's confirmed because we found the important shock deformation, plus Colonia at the outskirts of Sao Paulo. That is the Brazilian impact record. In Africa, we have a few more than in South America. It's 11 altogether in South America, and we have about 19 or 20 in Africa. But if you consider that the continental landmass is much larger for Africa, we are exactly on par. We have exactly the same number of known structures in South America as we have in Africa. There is scope for finding many more. These are the 2 basic geometric types of impact structures: simple bowl-shaped and complex. Simple bowl-shaped, cracked rocks of the crater floor, ejecta on the outside, and in the interior, different types of breccias, with melt, without melt, and so on. Same basic rock types, but collapse of the rim, moving material inwards, and rebound in these very strong, large impact events. The crust is depressed very strongly and rebounds and collapses then to form a central uplift, like Copernicus at the beginning of this talk. This is exactly what happens. We have the projectile penetrates into the target area, it implodes and forms a shock wave. A shock wave is a compression wave that moves material downward and outward. So we have ejection of material and compression of material. Eventually, this shock wave is caught up by a release wave when the material relaxes after being stressed very badly. We have melt developed, which lines the interior of the so-called transient cavity, the initial cavity, and here it is at its maximum diameter, and we got an overturned flap of material here, and then the transient cavity collapses and all this material is mingled in the interior. Now, in all likelihood, since crater formation, later post-impact sediments will be deposited on top, so that the apparent crater depth is exactly that, not the true crater depth, which would actually go to down here. Oops. One more, please. Voila. What now? Here we go. Still with the simple crater, we have the projectile. The projectile is totally deformed, melted, vaporized. Just to show you the pressures that are developed at the time, at the moment, or at the spot where the projectile disintegrates, more than 50 gigapascals, 500 kilobars, 1,000 kilobars. And then this rapidly decreases to the edge of the crater, obviously down here on the right and left as well. We vaporize material from the target, we melt material from the target, and we cause a series of transformations in the materials at these ultra-high pressures that the material experiences. This is not the normal pressure temperature regime that we experience in geological sciences, maybe to 1,000 degrees and 10 or 20 gigapascals to produce some eclogites or so. No, we go far beyond those pressures. The upper part of the target is being excavated, the lower part is displaced, pushed out of the way, it goes up here, and eventually it's mingled in the crater structure. And here we have essentially the same. Let's just look at the final result of a complex impact crater. We've got the terraced walls that I showed you on Copernicus. We have the central uplift. We have a sea of melted rock covering the interior. And we have ejecta, some of it falling back into the structure and some of it falling outside. Now, how can you recognize the impact structures in Minas Gerais or Sao Paulo or Goiás, other parts of the world? Does morphology suffice if you have a round form or a raised rim and inverse stratigraphy, a central stratigraphic uplift? The roundish form is not characteristic. A raised rim and inverse stratigraphy of the rocks from what you find outside of the crater is a very good indication that there could be an impact crater. And if you can prove that the rocks in the central uplift feature are stratigraphically uplifted, wonderful. Then look at the mineralogy and geochemistry below. In the meantime, one word about geophysics. It's been used a lot to study impact structures with gravity, magnetic, and seismic methods. The seismics are good because they may indicate a central stratigraphic uplift. The gravity and magnetics may show a disruption of the regional potential fields, but they by themselves are not diagnostic. The diagnostics comes from lab work. You have breccias, you look in the breccia for evidence of shock metamorphism, which I will give you. You try to find with geochemical methods remnants of the meteoritic chemical component mixed into melt-bearing rocks, and you look for the only megascopic to macroscopic telltale sign of impact structures, shatter cones. All of these I will show you now. The fundamentals of impact cratering. Classification of the impact-generated rocks. We'll do this quite quickly. It's so complicated when you see the next slide. And we'll talk a little bit more about shock metamorphism, about the deformations associated with the high pressures and associated post-shock temperatures. At 50 gigapascal pressure, the poor rock will experience also more than 1,000 degrees, much more than 1,000 degrees of temperature overprint. And here on the right, we have already a small, beautiful, intricate shatter cone, these divergent striations. And here we have two types of melt rock. This one from Africa, a little pebble, which was found at very small Tenemware crater. And here a massive melt sheet, about 80 meters high from Miss Destin. I think it's about 16 kilometers in diameter in Canada. So melt rocks are beautiful. I told you already, they may give us a meteoritic component, but on first glance, they could also be volcanic manifestations. And this is the impactite classification, which we will put away very quickly now. I just want to point out that we have two types. The distal formations around impact structures at far distances, and the proximal ones that we would find in and around the crater. Let's look at them in packages that can be swallowed easily. We have distal rock formations. For example, we have the Cretaceous-Paleogene boundary between Alaska and New Zealand in the Pacific. We have the KP boundary in Spain, in Denmark. We have it in Colombia and in the northeast of Brazil. And we may find associated with these ejecta layers melt blobs, tektites, and if they're very small, microscopic microtektites. Here are some. There's a piece of impact glass, which is actually different from tektites because it contains quite a bit of water. Tektites are dry. Tells us something about their process. These are associated with the Ries impact in southern Germany, but they were found 400 kilometers to the northeast in the Czech Republic, so-called Moldavites, because they were found close to the Moldau River. Impact glasses from the Nubian Desert glass field in Egypt. The name is Nubian Desert, but it's mostly in Egypt. And here we got some ergesites from another structure in Kazakhstan. Proximal is the actual area of the crater and the area surrounding the impact structure. We have impact melt. We got two types of breccias, lithic breccia, monomict and polymict, which is only composed of clasts, and we got something that contains melt particles as well. So we have a whole transition from impact melt to spheroid with melt particles and to lithic breccia without particles. And we first of all have the shocked rocks. Monomic breccia, polymic breccia, these are the lithic breccias. And then we have spheroid down here, not shown, and the melt rock. We have a granite. If it experiences 150 kilobars of shock pressure, compression, it still looks like a granite. But at 30 gigapascals, 300 kilobars, it looks more as if it's been too long in a washing machine. And at 45 gigapascal, we have evidence for melting. And it looks like pumice, like a volcanic glass with high density. It can float on water. A monomic breccia is exactly the same as a cataclysite. You got smaller and larger particles of one rock type. And it occurs everywhere in impact structures. For example, here in the Dala impact structure of 11 kilometers diameter in India. More interesting are the polymic breccias with or without melt particles. Here, without melt particles. Sandstone, gneiss, another piece of gneiss, some shale, some mylonite, granitic composition, different rock types, polymic impact breccia. But looking at the drill core does not tell you that it's impact breccia. I know that it's from Chesapeake Bay impact structure, but we need to do more work microscopically. Here we have the spheroid, which contains melt particles in addition to the clasts of lithic material. In this boulder, you can see all these amoeboid features, little blobs, dark gray. They are all melts, some with vesicles in them. And here we have a case from France, the Rochechouart impact structure, and we have melt particles here impregnated by secondary iron oxide. That's why they are dark brown. And the lithic clasts in part are reddish. But it's the same rock type. If this is an impact melt rock, 70% of this material is melt. The rest is clasts. An impact melt rock from Rotterdam, you can see the particles are getting smaller. Nice matrix of melt. Looks like a basalt with some vesicles, some crystals grown inside, but it does contain a meteoritic component. And here we have a clast-rich impact melt rock from Vredefort in South Africa. To get out of this. Another sample from Rotterdam, one from the Ries crater, with schlieren in it, material that has been partially melted. And here we have something that looks very similar to some of the samples returned from the moon. And I just want to point out that these rock types, swavite, lithic breccia, what we call a demic breccia, we can find on the moon, and we can find the Apollo collection of rocks, and we can find them on Earth in terrestrial impact structures. There are coherent impact melt sheets. There's this one here, the size of a large office building in Siberia, and this one here from Destin. The Siberian one contains a lot of diamond. There was a lot of graphite in the target, which under the high shock pressures was converted to diamond. Unfortunately, these little crystals are nanometer size and cannot be used for gemstone. Therefore, and because the structure is so far away from any transport infrastructure, this material cannot even be used as an abrasive. If you look at the thin section under the microscope of impact melt here from Lapajärvi in Finland, it just looks like some kind of basalt which has been polished in plain polarized light. Or other textures like intersertal that the students of geology have to learn in their Ignis petrology course. There are other types of breccias. I don't want to dwell on this for a long time, but there are dikes and veins in the basement of impact structures. Some of it is pseudotachylite, which those of you who worked with rock deformation or learned about rock deformation know as friction melt. And then there's something that looks like pseudotachylite, but could have different types of origin. And for example, the case of exposures of this material, massive exposures of this material in the Fredefort structure. And as long as we don't know what formed this rock, can give it a genetic name, we should call it just non-genetic PTB. Here we have 3 generations of PTB. Maybe one friction melt, the black stuff, the green, and an older one which is yellow. So we have 3 generations of melting, different compositions. But these 3 generations of melting occur within the Fredefort impact structure in South Africa. But which one dates the impact? Actually, the black stuff. The other 2 are pre-impact. Besides breccias generated by impact, there are many other types of breccias. Breccias is a brecciated, fragmented, jumbled up rock mass. There are sedimentary, tectonic, magmatic, and other breccias, all of which can occur in impact structures as well, as pre or syn or post-impact formations. And we need to look carefully, taking samples, look at the geological context, take samples, take them to the lab, and look for evidence that could tell us what they are. This diagram compares the temperature and pressure conditions that we have in normal geology, which is this little field here. And please note, both these scales are logarithmic. And these are the pressures that interest us in impact studies, up to vaporization from beyond 100 gigapascals. Here we got the eclogite field, maybe 25 gigapascals, and something less than 1,000 degrees, make it 1,100. Okay? We have important formations of impact diagnostic features, macroscopic and microscopic, in this field. This is once more the shock pressure zonation. At the outside of a crater, we just have elastic deformation, brittle deformation, which does not tell us what caused the effect. But if we find a concentric pattern, an annular pattern of increasing grades of deformation, well, then this is not tectonically caused deformation either. We have shock metamorphism. They are the irreversible deformation features in minerals and rocks. And we start out with something that is not diagnostic for impact, but if it occurs in high density and every piece of mica, like this biotite or this chloride here, has been deformed with these characteristic kink bands, then please look at the other minerals and maybe you will find some diagnostic impact features as well. Shock extension fractures are produced at very low shock pressures. This is 80 kilobars, which is in many labs, many petrological labs, the limit where they can crank up the pressure on rock samples of very small size. And we find typically in quartz-rich rocks this kind of pattern of short extension fractures. These quartz grains of about 1 millimeter in size each were crushed together and then after extension, and that's why I call them shock extension fractures, we form these intricate, short, irregularly shaped fracture patterns. There is no cleavage in quartz. We have all learned in first year geology studies. But impacted rocks show cleavage systems, so-called planar to subplanar fractures. In this case, 3 different orientations which are crystallographically controlled. Here another example of 2 systems. Planar fractures, but this is the most important feature. If you find something like this in quartz or in olivine for that matter as well, very densely spaced, maybe 5 to 10 micrometers apart or even less. These are the planar deformation features, and planar deformation features are our most important recognition criterion for impact structures. Sometimes we have fluid inclusions on them, which may give an indication that the impact occurred into water. We find those features a little anomalous, sometimes curved, sometimes we only find the fluid inclusions. In old rocks, Archean rocks, 3.2 billion year old rocks in Vredefort 2. And for a long time, this was the only thing that people described, and it was not quite clear whether it's impact deformation or not. Until in 1994, young man Uwe Reimold in France did some transmission electron microscopy and identified these features as twins, gemeas, in the quartz crystal lattice. Here, some nice ones on the lower left. And because they are oriented parallel to the 0001 orientation in the quartz crystal lattice, which is known as the Brazil twin system, these Brazil twins are characteristic evidence, and the first characteristic evidence that Vredefort was an impact structure. Why? Because Brazil twins only form in 2 processes: impact and hydrothermal growth of quartz from solutions. And because we're dealing with Archean granites, this was out of the question. They had crystallized from a magma, and they were a little older than the features, actually. Another telltale sign, and here are some of these aggregates of nanometric diamonds from poppygie. High-pressure polymorphs as the result of shock compression, solid-state transformation. We just jump from alpha quartz into the coesite field by adding pressure, or from quartz to stishovite at even higher pressures, or by crystallization from shock melt. If we are melting the whole system, we are up here. And then if we reduce the temperature, material under high pressure, for example here, this material was generated under 50 gigapascals, starts crystallizing. Here's my cursor here. And we enter the coesite field and we produce tiny crystals of coesite. Or in this case here, the beautiful mineral ringwoodite after olivine in a meteorite. And then, of course, zircon, which we all love for its chronological strength, one of the most important minerals in determining ages, it dissociates into bardellite, also known as zirconia, and silica, SiO2, and can also be an indicator of impact. We have thermal alteration features like these crystallographical controls on melting of plagioclase grains in the lower right as well, and Ballant quartz, probably formed from diaplectic quartz glass, which is a quartz glass not formed by melting as we know it, but by solid state transformation under pressure into a glass-like phase. We have mosaicism. This is a dunite shocked to 35 gigapascals, and we got all these little domains of different extinction under cross-polarized light. Here's another nice grain, and I will show you now. This is the unshocked counterpart. We have uniform extinction in all these grains. And here we have a meteorite from Mars in the thin section. I don't know what the magnification is, but all the plagioclase has been converted to glass, diaplectic glass. It still has all the deformation features that it had before the impact. And all the olivine shows typical shock mosaicism. So we have, maybe this is actually a pyroxene crystal. But most of this here in blue and green is olivine. Finally, at pressures above 40 gigapascal, individual minerals start melting, just like in partial melting in a magmatic system. Or at even higher pressures, the bulk rock melts and only few inclusions remain left over. We have many minerals which have been shocked experimentally to determine the pressure and temperature calibration for which effects take place at which shock pressure. PDFs, the most important features in quartz, form between about 10 and 30 gigapascals. Diaplectic glass from about 30 to 45 or 50, above that melting, and then finally we go into the field of vaporization. So this is shock metamorphism. It only gives you a 10-minute introduction, but if you see PDFs in any thin section, please call me or somebody else. Maybe you can confirm that you found a new impact structure. And if you find something like this here, shatter cones, in the case on the right, a meter long. I've shown you one before, which was only 5 centimeters high. Smaller ones here from Fredefort, and a beautiful 50 centimeter long piece of a structure in southern Germany. This is impact. They've never been described from any other geological setting. But there are features that can be mistaken, like this crystallization feature radially away from the nucleus, long crystals of the mineral stickite, which actually look, after erosion and weathering, a little bit like a shatter cone. We're nearly at the end. Next week, Professor Natalia Hauser will tell you a story about Araguaia, the largest known impact structure in the center of South America. These are the other structures. We have São Miguel de Tapuyo, which was confirmed last year by finding shock quartz. Paper still needs to be written. And I believe there's a student from Campinas working on this as well. Riachão, Serra Cangalha are written up in the literature, Santa Marta as well. Grace Oliveira, also from Campinas. She just graduated with a PhD, did this for her master a couple of years ago. Nova Colinas, we have the data, we just need to publish it. Should hopefully happen towards the end of the year. Colonia, near Sao Paulo, looks like an impact structure. Some people talk about it like an impact structure, but the final proof in terms of shock metamorphism has not been given. And the structure needs to be drilled to prove its origin, as well to get a full transect, a full drill core to 400-meter depth or so through the crater's sediments, which have been a closed basin depository for biological, climatic, and paleo-environmental information. Maybe the structure is as old as 5 to 10 or more million years, and we could get a fantastic long-term paleoclimatic set of data. We have 3 structures in the south of Brazil: Vista Alegre, Vajão Dome, Cerro do Jarau. They are all unique. They are, with the exception of 1 or 2 other structures in the world, only one of them in India is accessible, Luna, and is much smaller than these structures. These 3 are formed in basalts of the Prana Basin. And impact into basalts is something that has happened over and over again on other planetary bodies. Venus, Mars, and in other places too. And therefore, a lot of people are actually evaluating these 3 impact structures to learn more about impact into natural basalts. Beyond that, we have a small field of little craters, maybe 100 meters long, 40 meters wide, at Campo del Cielo, where we have this fantastic patrimonio argentino of the Campo del Cielo meteorites, some of the largest meteorites ever found on Earth. Rio Cuarto is debated. Some people want it to be a crater field, long and elongated, and another group, or 2 other groups, have said no, these are aeolian deflation features. Consistent winds coming off the Andes have deflated the soft blurs in this area of the Rio Cuarto state in Argentina. And tiny Monterrey in Chile, northern Chile, 400 meters in size, an interesting structure which I really personally would like to see. If we are linked into Argentina, there are reports about many impact structures in this area here, the Bajada del Diablo. And I tell you, there is no evidence for impact. If there was impact, the evidence still needs to be presented. Therefore, they have not been plotted here. And with that, I'm thanking you for your attention and invite you to ask questions. Here's the announcement of the talk for next week. This is Araguinha, actually, a 40-kilometer structure, again with a tandem X and Sentinel-2 data, digital elevation model. The collar around the central uplift basin here, the Araguaia River flowing around. Here's the city of, or the town of Ponte Branca, and Araguinha is located somewhere over here. Okay, that is directly at the border between Goiás to the east and Mato Grosso to the west. The river here forms the border. Thank you very much for your attention.
Thank you very much, Uwe.
I try to get back to you, okay?
Okay.
We can manage.
We have lots.
There you are. Hello.
Hello. I have lots of curiosities because
Okay.
in an amazing world, an amazing structural world, geochemical world. So, but I'm so sad because if we don't find a shatter cone, no chance to have found an impact crater. Shatter cone, so impact crater one.
Come to Araguinha. They are there.
Yeah.
And
But
there are many impact structures where we've never found shatter cones either.
Okay.
What you need is fine-grained target rock. If you have a coarse-grained target, it's not easy. Actually, it is not easy to make nice shatter cones, but can be easily identified.
Okay.
You want limestone, you want a siltstone or shale or something like that. That's in Araguinha. We have the fine-grained, relatively fine-grained meta sandstones, probably of Cuiabá group origin. They have shatter cones.
Okay. So, in the difference between the fault breccia and breccia from impact, I think is a little bit complex just in the field.
The volcanic crater versus the impact crater. I said before, if you have a stratigraphic uplift in the center, but then the structure has to be more than 4 kilometers in diameter. That is a very good piece of evidence. And maybe you get this actually from seismic work, also in areas where craters are completely covered and so on. For example, Saudi Arabian Peninsula. The overturned flap at the edge of the crater. Normally in a volcanic crater, you may find slight flexure of material at the edge, but it will not be overturned like this, so that you actually on top have an older stratum and the younger one underneath. That would be a telltale signal. And otherwise, you need to take samples. You need to take them into the lab, make many thin sections. Nova Colinas has not been easy to confirm.
Okay.
You may know that somebody from the CPRM has just published a paper about Nova Colinas in the journal of the CPRM. He has no evidence for impact. He's got a lot of nice imagery, remote sensing data, and some geophysics as well. And he refers to 2 older pieces of work also. No evidence for impact. We do have something like 40 samples of sandstone from Nova Colinas, and only 3 samples gave us a lot of grains of quartz with shock deformation. We've got to keep searching and searching and searching. You know that I let the rabbit out of the hat. Tell the public about Nova Colinas. Now we have to really write this up. But it was difficult. And with São Miguel de Tapuyo, it's been 10 years for Alvaro Costa and Marcos Vasconcelos and some others in the group. They never found anything shocked in the samples they came back with. It was last year that they collected 2 samples of brecciated sandstone. We made high quality thin sections and we found shock quartz. And then he reported this, or maybe 2 years ago already, he reported this at the last SPG Congress in Rio de Janeiro.
I understand. And the King's Band are always in the quartz?
You saw king bands in biotite. There was a picture from my MSc in chlorite from dunite, actually. And you saw the picture on the left, which was gray, which I did not talk about. It was a feldspar. So you can actually have king bands in tectosilicates as well.
But just in minerals.
Yeah.
Just in minerals. In outcrops with, yeah?
No, you would only find this microscopically.
Okay. Yeah. So I think it's some question in the chat. Raquel?
Yes. Yes, we have some questions.
Sure.
And the first is...
Hola.
You hear me?
I can hear you very well. Maybe the others too?
Yes, now yes.
Yes. And Luciano Alessandretti asked, how can the maximum distance between the impact site and the development of soft sediment deformation structures can be estimated?
Wait, this is a difficult one. You don't need much in terms of stress to produce soft sediment deformation. But to my knowledge, so millipascals or megapascals would be more than enough. You don't need kilobars and gigapascals to do this. But to my knowledge, there is essentially no literature out there people have looked far away from impact craters or impact structures in the complex type for soft sediment deformation. But there's one case. We have been to another crater named according to an oil company in Libya. About 80 kilometers south of BP is the Libyan state oil company Oasis. It's a structure that everybody wants to make 12 to 15 kilometers in size. But I found soft sediment deformation uniquely in the northeast quadrant at 18 kilometers away from the center of Oasis. We have not published our findings. We could not complete the fieldwork because in 2010 we were there, and in 2011 the so-called Arab Spring caught up with Libya, and they've had civil strife, civil war ever since. We could not go back, so it's not been published. And I cannot prove, unless I find something like this a little closer by and nothing further away, that this soft sediment deformation is linked with the Oasis impact. But interesting question.
Okay, thank you. And there is one more.
Okay.
From Felix Nanini. And is there some relation between latitude and the frequency of extraterrestrial impacts on Earth?
It may look that way. On the crater map that I showed you, there were not too many crater structures at equatorial latitudes. But I think it should not be obvious. If we had better opportunity or better possibilities to study or to look and search for impact structures along the equator, we would probably have more impact structures there as well. We have still the dense vegetation in Amazonia, which has made remote sensing and ground-based study very difficult. We have rainforests in Central Africa as well. Countries like Gabon, Cameroon, Nigeria, and others along the equator have not been easy places to go to and look for impact structures. And many other impact structures in the central belt around the world have civil war. I don't want to go to Chad. I don't want to go to Mauritania. I don't want to go to Niger, Burkina Faso, South Sudan, and so on, because of civil war in all these countries, which is hindering geological exploration and makes life miserable for 1 billion people. We have a lack of impact structures in China. I've just received a report of maybe a second small impact structure having been discovered in China. Well, it needs to be examined now. The other one is a 1.4 kilometer structure that's confirmed close to the border with North Korea. But the bulk of China has not given any impact structures yet. We will find further ones. We will have more discoveries. And I think this picture of lack of impact structures in the low latitudes is going to change with time. The rate of discovery is 2 to 3 impact structures per year. Some years none, some years 5. Yeah, it will take time. Thank you for the question.
Okay, thank you. And for now, we don't have more questions, but I'd like to say that the lecture was really good, and I'd also like to thank you for accepting our invitation to join us at this event.
Prazer. I'm very happy to be able to do this, to have been able to do this. Do we have other questions from other people still? Thank you, Raquel.
Thank you so much.
Thank you, Uwe. Thank you, Raquel. I have one more curiosity.
Okay.
Have chains of craters been recognized on the planet Earth?
A what?
Chains of craters.
Change of crater?
Chains.
A chain.
This is not really good, I know.
No, the crater chain. Let me think about this. No, I don't think it has. There are several cases where there are two craters close together. There's one in southern Germany, the Ries crater in Steiner Basin. They are about 45 kilometers apart, but there's no third or fourth. We don't know whether they were formed by independent asteroids or whether the asteroid broke up upon entry into the atmosphere, but they are a little far apart, 45 kilometers. It's a bit far if you calculate the triangle from breakup in the upper atmosphere to the ground. You only have very limited time to do this. There's Clearwater East and West, which has just been shown probably to be totally unrelated. And I was supposed to talk about Sudbury a little more, and I forgot. You remember there was a lake with a W in the upper right of the Sudbury picture. It's another crater called Vanapitei, and that is 2 billion or 1.8 billion years younger than Sudbury. Sudbury is the third oldest impact structure in the world at 1.8 billion years, and Vanapitei is 35 million. But that's all. We don't have chains. And we don't want chains either. We don't want bombardment along a chain in a densely populated area on Earth. But interesting question. But we see them on several planetary bodies in the solar system, Jupiter, Ganymede, and in other satellites of Saturn and Uranus as well. Pame, other question? William?
Tem mais uma. There's more questions in chat.
Yeah, something about clastic dikes.
Yes.
Yeah.
But I don't quite understand what this refers to. We have duplication. Oh, it's maybe a question about the overturned flap at the edge of the crater. Whatever was originally there horizontally would now be overturned. And in between, you would find the crater structure developed. If there are clastic dikes, if they are turned over 100%, they may well be still dike features. But if they are only upturned, it would still be dike features. So I would not expect duplication, but maybe disruption of dikes due to the extension associated with the general extension of the target area.
Okay.
All right. Maybe you guys can Google. You're welcome to Google my mail address.
Yes, would be
Uwe@gmail.com. Okay, just go to UnB and look for personnel, docentes. You find it there, and you can email me if you have further questions. I would be happy to reply.
Oh, perfect. Many, many thanks to you, mainly to the equipe also.
Yes, from me too. And
so
thank you.
We'll
see
the next week with Natalia.
Definitely. Should be a good one, but
yes, of course. Many thanks.
She's talking really about Brazilian impact structures. I did not have time today.
Yeah,
so,
no, it's too much.
It's
okay.
Thank you, all of you,
Many thanks.
for inviting me and for attending the talk, questions and everything. And yeah, it was good fun. Thank you.
Good. Thank you. Bye bye.
Thank you. Bye bye.
Bye, everybody.